Welcome to Key Safety Talks on YouTube.
Great to be here.
Today we're tackling something really critical. Understanding how hazardous materials actually move through the air when they're released.
Yeah, and the potential impact they can have. It's pretty essential stuff for anyone interested in safety, emergency preparedness, really anyone near an industrial site.
Absolutely. Think of this as, well, essential knowledge.
Exactly. And we're drawing on some pretty comprehensive sources today, detailed notes, a whole chapter on toxic release and dispersion models.
Okay, good. So what's the goal? What should listeners take away?
Well, the main thing is to pull out the key safety lessons, try to make sense of the calculations without getting bogged down,
That's understandable, right?
Yeah, and look at some real-world examples. The sources mentioned Bhopal, for instance, and other scenarios that really drive home why this all matters.
Okay, so let's get into it. First off, this term, toxic release model. What exactly are we talking about? Sounds technical.
It is a bit technical, sure, but the idea is straightforward. It's essentially a tool, a method facilities use to estimate what might happen if there's a release.
Estimate what? Specifically?
Yeah.
The effects.
Exactly. The effects of a toxic material release, both right there at the plant site and, crucially, in the surrounding community. It helps predict the consequences.
And you mentioned Bhopal earlier. How does a tragedy like that fit into why these models are so important?
Well, Bhopal is just a devastating example of what can go wrong. A massive, uncontrolled release.
Right.
It really forced everyone to confront the potential scale of these disasters. It highlighted, tragically, the absolute need for solid emergency planning.
And better facility design too, presumably.
Definitely. Designs that minimize the chances of a release and limit the consequences if one does happen. These models are fundamental to that whole process.
It really makes you think. Could better modeling have changed anything back then?
Right.
Prevention. Response.
It's a tough question, but it certainly emphasizes the value of these predictive tools today.
Okay, so say a release occurs. What are the first steps in modeling what happens next? The consequence modeling.
Right. Generally, there are three key steps to start with. First, you have to identify the potential release incident itself.
Like, how could it happen? A broken pipe? A tank failure?
Precisely. What process situations could lead to a release? Second, you need what's called a source model.
Source model.
That describes the release itself. What material is it? Is it a gas, a liquid?
Yeah.
And importantly, what's the rate? How much is coming out per second or per minute?
Got it. The what and how fast.
Exactly. And the third step is the dispersion model. That's where we estimate the downwind concentrations.
So that tells us where it goes and how strong it is.
That's the core idea, yes. How it travels and mixes with the air.
So dispersion, it's obviously more complex than just knowing the wind direction, right?
Oh, absolutely. The atmosphere is a busy place. Several factors really shape how these materials spread out. Well, wind speed is a big one, obviously. Stronger winds carry things further, but they also tend to dilute the plume faster.
Okay, that makes sense. What else?
Atmospheric stability. This is really crucial.
Stability. Sounds like weather forecasting.
It's definitely related. It essentially describes how the air temperature changes with altitude.
And why does that matter for dispersion?
Because it governs how much the air mixes vertically. You can have stable conditions, unstable conditions, or neutral conditions.
Okay, break that down for me. Stable versus unstable.
Sure. So stable conditions often happen at night. Clear skies, light winds. The air near the ground is cooler and denser than the air above it.
So it doesn't want to rise.
Exactly. Vertical mixing is suppressed. It's like there's a lid on the lower atmosphere. Smoke, for example, tends to stay in a concentrated plume and drift.
Okay, like a layer. And unstable.
That's more typical of a sunny day, especially with light winds. The sun heats the ground heats the air right above it.
And hot air rises.
Right. So you get lots of vertical mixing, lots of turbulence. Smoke on a day like that tends to break up and dissipate much faster.
That's a helpful visual. Is there a way to categorize this?
Yes, there is. A common system is the Pascal-Gifford system. It uses letters A through F.
E to F.
Yeah, where A is extremely unstable, lots of mixing, and F is very stable, very little mixing. It gives modelers a way to quantify that atmospheric stirring.
Got it. A is like a boiling pot. F is like still water.
That's a good way to think about it.
Okay, so wind speed, stability. What else influences the spread?
Ground conditions make a difference too. Buildings, trees, hills, any obstacles.
How so?
They disrupt the airflow near the ground, creating what we call mechanical turbulence. This extra churning tends to increase the mixing.
So a city environment would mix things more than open fields.
Generally, yes. Smooth, open terrain allows for less mixing compared to a complex urban or forested area.
Interesting. Anything else?
The height of the release is important.
Higher is better.
Usually, yes, for ground-level concentrations. A release from a tall stack has more time and atmosphere to mix and dilute before it reaches the ground.
Ah, that's why industrial stacks are so tall.
It's a key reason, yes. Gives it a head start on dilution.
Makes sense.
And finally, the properties of the material itself matter its initial momentum and buoyancy.
Momentum and buoyancy. How does that play in?
Well, think about a gas being released under high pressure. It has momentum, right? It shoots out.
Okay.
Or if it's a very hot gas, it's buoyant, it wants to rise quickly. This can effectively increase the release height.
Like a hot air balloon.
Sort of, yeah. But conversely, if you release a vapor that's much heavier than air, maybe because it's very cold or just has a high molecular weight,
It sinks.
it tends to sink initially, yes. It might spread out close to the ground before it starts mixing upwards effectively, so its initial behavior is quite different.
Okay, that's a lot of factors.
Yeah.
Does this lead to different kinds of dispersion we need to model?
Broadly speaking, yes. We often talk about two main types. First, there's neutrally buoyant dispersion.
Neutrally buoyant, meaning it just drifts with the air, not really rising or sinking on its own.
That's the idea. The mixture of the released gas and the air it mixes with becomes roughly the same density as the surrounding air.
So its own weight isn't a big factor anymore.
Right. At that point, its movement and spread are mainly governed by the existing atmospheric turbulence, the wind, the stability we talked about. Any initial push or lift becomes less important over time.
How do we model that type?
There are two main approaches. For a steady, continuous release, like a constant leak from a valve, we often use plume models. They estimate the concentration at different points downwind within that steady plume.
Okay, and for a sudden release, like a tank burst.
For that, we use puff models. They track how a single instantaneous cloud or puff of material disperses and dilutes as it travels downwind.
Zooms and puffs.
Got it. And models like the Pascal-Gifford approach we mentioned, using those stability classes and wind speed, are often applied here, especially for gases where turbulence is the main driver. They help estimate how much the plume or puff spreads horizontally and vertically.
Okay, so that covers the go with the flow gases. What about those heavier ones you mentioned?
Right. That brings us to dense gas dispersion. This is for gases that are significantly denser than the air around them.
Why would they be denser?
It could be their molecular weight is just higher than air's, or maybe they're released as a very cold vapor or liquid that evaporates, making the resulting gas cold and dense.
And gravity takes over.
Gravity plays a much bigger role, especially initially. A dense gas cloud tends to, slump.
Slump.
Yeah, it spreads outwards along the ground, becoming wider but shallower near the source. Gravity pulls it down and makes it spread horizontally.
So it hugs the ground more.
Initially, yes. And there's also a lot of mixing right at the start as this heavy gas pushes into and displaces the lighter ambient air. It's driven by that density difference.
Sounds quite different from the neutrally buoyant case.
It is, particularly near the release point. Eventually, though, as it mixes with more and more air and gets diluted.
Becomes less dense.
Exactly. It transitions towards behaving more like a neutrally buoyant gas, and atmospheric turbulence becomes the dominant factor again for further dispersion.
Are there specific models just for these dense gases?
Yes, definitely. Our sources mention models like the Brummer-McQuade model, for example. These are often developed using experimental data specifically capturing that initial gravity-driven slumping and spreading behavior.
Do they have limitations?
They do. It's important to know them. For instance, the Brummer-McQuade one, as described, is best suited for ground-level releases on flat terrain and uses wind speed at a specific height, like 10 meters.
So you need the right model for the situation.
Absolutely. The key thing with dense gases is remembering that extra influence of gravity and density, especially close to the source.
This is all very detailed about concentrations. But how do we actually know what concentration level is dangerous?
Good question. That's where things like ERPGs come in.
ERPGs.
Emergency Response Planning Guidelines. They're basically established exposure guidelines.
Guidelines for what?
For the maximum airborne concentration of a specific toxic chemical that the general public could be exposed to for up to 1 hour without experiencing certain levels of health effects.
Okay, so they're like safety benchmarks based on health impacts.
Exactly. After we use the dispersion models to predict concentrations downwind, we compare those concentrations to the ERPG values for that chemical. It helps assess the potential hazard.
Who sets these guidelines?
They're developed and published by the American Industrial Hygiene Association, AIHA, and they're specifically intended for the general population, not occupational exposure limits.
Are there different levels of ERPGs?
Yes, there are 3 main levels: ERPG1, ERPG2, and ERPG3.
What's the difference?
Okay, ERPG1 is the lowest level. Below that concentration, pretty much everyone should be okay for an hour, maybe experiencing only mild temporary effects like an objectionable odor, perhaps.
All right, noticeable but not harmful.
Generally, yes. Then ERPG2 is a higher concentration. Exposure below this level for an hour shouldn't cause irreversible or serious health effects or symptoms that would stop someone from taking protective action, like getting away.
Okay, more serious potential, but still escapable without lasting harm.
That's the idea. And ERPG3 is the highest level. Below this concentration, exposure for up to an hour shouldn't be life-threatening for most people. Above ERPG3, you're definitely in a zone with potential for life-threatening effects.
Wow, okay. That really clarifies the danger levels.
And yeah, you can look these up. There are specific ERPG values published for hundreds of different chemicals. They're often found in tables, like Table 5-6, mentioned conceptually in our source material.
So when you see those maps sometimes with circles or zones drawn around a facility showing risk areas, is that based on this?
Very likely, yes. You're probably thinking of isopleths.
Isopleths?
Yeah, an isopleth is just a line on a map connecting points that have the same value. In this case, the same concentration.
Ah, like contour lines on a weather map show equal pressure.
Exactly the same principle. So, after running a dispersion model, you can calculate where, say, the ERPG2 concentration level is predicted to reach. Then you draw a line connecting all those points.
And that shows the boundary of that hazard level.
Precisely. It defines the predicted spatial extent, the footprint of the hazardous cloud for that specific concentration threshold. You can draw isopleths for ERPG1, NEGATS2, and MEGATS3 to show different zones of potential impact.
Does that work for both plumes and puffs?
Yes, the concept applies to both continuous plumes and instantaneous puffs, though the calculations and the resulting shapes might be different.
And ground level ones are most important for people.
Definitely. Ground level concentrations and their corresponding isopleths are usually the primary focus for assessing the impact on people, buildings, and the environment nearby. Emergency planners use these maps extensively.
Okay, that makes a lot of sense. It visualizes the model output.
It translates the numbers into a geographic area of concern.
So, given all this potential hazard, what can facilities actually do to prevent releases or lessen the impact?
Mitigation, right.
Exactly. Mitigation strategies are absolutely key. The idea is to lessen the risk either by preventing the release from happening at all or by reducing the consequences if it does.
Acting on the source, you mean?
Acting on the source, or on the release itself, or even along the pathway it might travel.
What kinds of strategies are we talking about? Is it all just engineering?
Engineering is a big part, but it's broader than that. We can categorize them. One approach is inherent safety.
Insurance safety.
Yeah, basically designing the hazard out or reducing it fundamentally, like using less of a hazardous chemical inventory reduction, or maybe substituting it with a safer alternative altogether.
Making it less dangerous to begin with.
That's the ideal, yes.
Yes.
Then you have engineering design controls. This is about building safety into the plant itself.
Like what?
Stronger pipes and tanks, better process controls, installing emergency shutdown systems, maybe secondary containment like dikes around tanks to catch spills, building robust systems.
Right. Then there's the management side. This involves things like having really good operating procedures, thorough training for everyone.
People and procedures.
Absolutely. Regular audits, inspections, equipment testing, careful management of any changes made to the plant or process. All that administrative stuff is vital.
Okay, what else?
Early detection is another layer. Sensors that can pick up vapors quickly, alarms, personnel trained to spot the signs of a leak.
Catching it before it gets big.
The sooner you know, the sooner you can react. And then there are countermeasures, things you do immediately after a release starts.
Like damage control.
Kind of.
Yeah.
Using water sprays to knock down a vapor cloud, maybe setting up water or steam curtains to try and contain the spread, diluting the cloud with air, using special foams on liquid spills to reduce evaporation.
Active responses.
Yes, and in some very specific cases with flammable clouds, maybe even deliberate controlled ignition, though that's complex.
Wow. And finally, emergency response planning.
Critically important. This covers everything from on-site communications during an emergency to clear evacuation plans, designated safe havens, ensuring people have the right personal protective equipment, PPE, medical treatment plans.
The whole emergency plan.
Right, and practicing it. Drills, training, making sure everyone knows their role. It's a whole system.
It really sounds like safety is built in layers.
It has to be. And it's worth stressing that all these mitigation options are considered part of that overall consequence modeling picture. You model the release and you model how effective your mitigation might be.
Right.
But the sources are clear. Prevention is always better than cure. Trying to react effectively once a hazardous cloud is moving downwind towards a community? Well, time is incredibly short and the potential impact can be severe. Inherent safety and robust engineering are paramount.
This has been incredibly insightful. Really paints a picture of the science and the sheer amount of planning involved in managing these risks.
It's a complex field, definitely. But understanding the basics, dispersion factors, modeling types, ERPGs, mitigation, it's crucial.
Yeah, it highlights why understanding these concepts is important, not just for engineers, but really for broader safety awareness in communities near industrial areas.
Absolutely. This knowledge helps everyone appreciate the safety measures in place and why they matter.
So just to quickly recap the key things we covered. We talked about what drives dispersion wind, stability, the ground, release height, and type.
Right, and the difference between how neutrally buoyant gases and those heavy, dense gases behave.
Then the ERPGs, those health benchmarks.
And how they relate to isopleths, those hazard zone maps.
And finally, that whole range of mitigation strategies, from inherently safer design right through to emergency response.
Exactly. It's a multifaceted approach to managing risk. Hopefully, this gives listeners a better framework for thinking about these issues.
I think it definitely does. It certainly makes you appreciate the layers involved in trying to keep things safe.
It does, which kind of leads to a final thought, perhaps.
Go on.
How can we collectively use a deeper understanding of these dispersion and mitigation concepts to push for even safer workplaces, safer processes, and ultimately safer communities?
That's a really important question to ponder. How do we translate this knowledge into continuous improvement?
Something for everyone to think about in their own context, maybe.
Definitely. Well, thank you for walking us through all that. It's been incredibly valuable.
My pleasure.
And thank you to our listeners for tuning in. We hope this discussion helps you better understand this critical area of safety and emergency preparedness.